Welcome back, everyone, to our continuation of additional trigonometric identities. In this video, we're picking up exactly where we left off last time. Last time, we discussed section 5.2 and introduced the sum and the difference identities. In this section, we're going to still keep into the same handout, but here, pick up on page 4, where we're going to introduce section 5.3's content on the double angle, power reducing, and half-angle identities. Although this seems like a lot of new identities, in all actuality, they're kind of all the same exact set of identities, just sort of algebraically manipulated. In the grand scheme of new identities that we're running into, arguably, these first two are some of the most important. If theta is going to be a given angle, we're going to now define the double angle formulas. That's what these are going to be. The double angle formulas allow us to now get an understanding of what, for example, sine of 2 theta, cosine of 2 theta, and tangent of 2 theta are. If any of you intend to go on to take something like calculus, especially if you go on to take something like calculus 2, these types of identities start popping back up when you least expect them. In particular, these first two. Sine of 2 theta is equal to 2 times the product of sine and cosine. And the cosine of 2 theta, you actually have some freedom with. There's 3 different identities to work with. The baseline identity is that cosine 2 theta is equal to cosine theta minus sine, or cosine squared theta minus sine squared theta. However, if you use the Pythagorean identity to swap one of these cosine or sine squareds out for the other, you can rewrite this as either 2 cosine squared minus 1 or 1 minus 2 sine squared. These new formulas we're running into now open up even more angles that we can find the sine and the cosine of. To begin with, let's take a look at another type of example that we've sort of been playing with more than a few times so far. Suppose you know that the sine of an angle is 4/5, and you know that that angle lives in quadrant 2. So of course we can draw a picture of that angle. Here we are in quadrant 2. The angle then is here, theta. Sine of it is opposite over hypotenuse, that's 4/5. And if you use the Pythagorean identity, you'll realize the base is -3. After having drawn this picture, we ask what the sine, cosine, and tangent are of 2 times this angle. Well, it turns out we can use the identities to help get this done. Sine of 2 theta is equal to 2 sine theta cosine theta, and from this picture, we know that cosine is -3/5. Sine was given to us as 4/5, and so their product gets us to the finish line. Cosine 2 theta runs around, and I'm going to use the baseline version of that, which is cosine squared theta minus sine squared theta, because I already know those quantities. The cosine was -3/5, now it's squared, minus the sine, which was 4/5, now squared. And so this would turn into 9/25 minus 16/25. And you can simplify that as much as you'd like. The tangent also has a formula. Tangent 2 theta is 2 tangent over 1 minus tan squared. And so then here it would be equal to, writing that down, we have 2 tangent theta over 1 minus the square of tangent. And by looking at this picture, we know the tangent is, of course, opposite over adjacent. So here we're getting 2 times -4/3 over 1 minus its square, which is, of course, 16/3. And you can, 16/9. And, of course, you can simplify that as much as you'd like. We can tackle very similar problems like we saw in the last video. For example, what's the exact value of cosine squared of 15 minus sine squared of 15? As it stands, finding the sine or the cosine of 15 degrees is hard. Last lecture, we did introduce this idea of you could, for example, rewrite cosine of 15 degrees as the cosine of 65 degrees, or we said 60 minus 45 is what we did. So let's do 60 degrees minus 45 degrees. And then we used a difference formula, but that seemed kind of cumbersome. It might be easier to simply look at this formulation and say, oh, okay, I know what this is. I could sit here and say that this is clearly equal to cosine squared minus sine squared. This is going to be a cosine of 2 times whatever the angle is. Because remember, that's the formula here. No matter what the theta is, if I have cosine squared of theta minus sine squared of theta, this can be replaced with cosine of 2 times that theta. So in this case, the theta in question is 15 degrees. So this is going to be cosine of 2 times 15 degrees, which is, of course, just cosine of 30 degrees, which we know is equal to root 3 over 2. So what we're starting to come up against, the fact that there's more than one way to proceed with a trig problem. We could have done what we learned last lesson, or we could have done what we've learned this lesson. In the real world, you get the freedom to choose how you proceed. And that freedom is both a blessing and a curse. On one hand, you have a lot of tools in your toolbox, but on the other hand, it's hard to learn to figure out over time which tools are more appropriate for what instances. So, if we can answer these types of questions, using the double angle formulas, can we also verify trig identities with the double angle formulas? And it turns out the answer is yes. In fact, mixing what we learned last video and what we're learning this video, we can actually build really, really interesting trig identities for more complicated looking objects. For example, here's an identity. The sine of 3 theta is equal to 3 sine theta minus 4 sine cubed theta. This one, if you just sort of encounter this in the wild, you would probably be skeptical that this is true, and moreover, you might even have some difficulty determining that this is true. With the knowledge that we have right now, we know, for example, some indifference formulas, we know some double angle formulas, we know these are sort of tools we might want to be looking for. But if you weren't pointed in that direction, this one might be a little difficult. If you do want to pause the video and take your own sort of crack at it, I really encourage you to do so. If you do get stuck, that's okay. Feel free to sort of hit play for a little bit, watch a few seconds, see what the next step I do is, and then hit pause again and see if you can't make it to the end. This one's a really good challenging problem to make sure you're understanding a lot of the tools that we're working with. The correct way to start here is to actually start with the sine 3 theta. Although the right-hand side looks more confusing, you're going to have a lot of difficulty going from regular sines to sines of multiple angles. So the best way to start here is to start by taking sine of 3 theta and actually realizing it as the sine of 2 theta plus theta. This is important because with this point of view, you can imagine that 2 theta is your alpha, and you can imagine that a regular theta is your beta, and so this is a sine of alpha plus beta. And using a sum formula from the last video, we can now rewrite this as sine of alpha, which is sine of 2 theta, times the cosine of beta, which is just theta, plus the cosine of alpha, which is 2 theta, times the sine of beta, which is just alpha. When we write it this way, we have sines and cosines, which we're happy with, and then we have some double angles, sine 2 theta and cosine 2 theta, which now, within the context of section 5.3, we can use the double angle formulas to help reduce this. So the sine 2 theta becomes 2 sine theta cosine theta times the cosine theta here, plus cosine 2 theta, which I'm going to use the base version. I'm going to use cosine squared theta minus sine squared theta times sine theta. So if you're confused at all with what I've done, I'll use some highlighting here. The sine 2 theta has turned into this bracket, and the cosine 2 theta has turned into that bracket. I'm now going to multiply everything together. The right one will require some distribution. I should end up with 2 sine theta cosine squared theta plus sine theta cosine squared theta minus sine cubed theta. You might have observed while I was writing this out that indeed this first term and the second term are actually both like terms. We can combine those and turn those into a 3 sine theta cosine squared theta minus sine cubed theta. And then one of the last moves to make is to realize that our objective only has sines in it, and so this cosine squared has got to go. Using the Pythagorean identity, I'm going to rewrite the cosine squared as 1 minus a sine squared. So just to be clear, just to clarify here, I rewrote the cosine squared as 1 minus sine squared. One last distribution will give me then 3 sine theta minus 3 sine cubed theta minus sine cubed theta, which then will combine, and I'll get my 3 sine theta minus 4 sine cubed theta, which is exactly what I wanted. So there's a lot of moving parts in this trig identity, and it kind of pulls together a lot of the information that we've done so far. If you did pause the video to try to work through components of this on your own, and you weren't able to make it all the way to the end, that's okay, we're still learning some of this content. But eventually, by the end of the course, this is the sort of caliber of trig identity verification that I'm hoping for everybody to be able to obtain. So what we've learned in section 5.3 so far is some of the double angle formulas, but we can actually sort of get some more out of those double angle formulas. You might notice, for example, that these representations of cosine 2 theta all involve some squares. So what I might do is I could take these formulas that are all equal to cosine 2 theta, and I could solve for cosine squared or sine squared. And that'll allow me to, for example, replace sine squared with some sort of an algebraic equation involving cosine 2 theta. And so if you're working within the context of a problem where squares are bad, but multiple angles are good, that might be something you're interested in. That's what brings us to the power reducing formulas, which is what we have here. Sine squared is equal to 1 minus cosine 2 theta over 2. Cosine squared is 1 plus cosine 2 theta over 2. The tangent squared, of course, is sine squared over cosine squared, so the 2's cancel and we get this representation. These are known as the power reducing formulas. One of the more common classes in which these are utilized is, again, if any of you go on to take Calc 2. These types of formulas pop up a lot because there are certain mathematical operations where doing it to a sine squared or a cosine squared is very cumbersome, but it's very easy to handle these formulations. So if we have something like a sine squared and a cosine squared formula, a question you can ask is, can we get sort of a reducing formula for higher powers? And the answer is yes. For example, we can do all even powers. The simplest additional even power, of course, is something like sine to the fourth, because sine to the fourth is just sine squared squared. So one exercise we could work through is taking sine squared and rewriting it with no higher powers. So that is, we're going to rewrite this in such a way that it does not contain powers of trig functions greater than 1. The way to do this is to proceed exactly as I indicated in the beginning. You should start by noting that sine to the fourth of theta is, of course, none other than the square of the square. Sine squared has its own formulation as 1 minus cosine 2 theta over 2. So that's the same as 1 minus cosine of 2 theta all over 2 quantity squared. Which I'm just going to pull that 1/2 out because that's just going to go along for the ride. So we're going to get the square of 1/2 is 1/4 times 1 minus cosine of 2 theta squared. If I FOIL that, I should now get 1/4 times, I'll get 1 minus 2 cosine of 2 theta plus cosine squared of 2 theta. Now my objective is to make sure I don't have any terms with powers of trig functions greater than 1. So these terms over here are great because I only have powers of 1 for my trig functions, but this term is no bueno. Notice, however, that if I were to call the inside of this function alpha, then cosine squared of alpha is equal to, well, by using this other power reducing identity, that's equal to 1/2 times 1 plus cosine of 2 alpha. Now, the important and interesting observation is that this alpha is actually 2 theta. So when I rewrite cosine squared of 2 theta, I'm going to rewrite it as 1/2 times 1 plus cosine of not 2 alpha, but since alpha is 2 theta, it's going to be 2 times 2 theta. And that's going to be 4 theta. So this is going to be equal to 1/4 times the quantity 1 minus 2 cosine of 2 theta plus 1/2 times 1 plus cosine of 4 theta. It's important to note here that this is a 4, not a 2. And that's because the previous line's cosine squared had a 2 in it already. So when I use this formula up here, I was multiplying by an additional 2. At the end of the day, this is a nice formulation of sine to the fourth such that every present trig function has no power greater than 1. Now I could distribute the 1/2 and the 1/4 and clean this up a little bit if I want to, but simplification is not necessary. We have one last handful of identities to run up against in section 5.3, and that's going to be what's called the half-angle identities. The way to get the half-angle identities is we're going to take these power-reducing ones. We're going to replace these thetas with theta over 2's, which will then make these 2 thetas just turn into regular thetas. And then to get rid of the squares, we'll take some square roots. In doing so, we get the half-angle formulas. That is, if I want to compute the sine of theta over 2, I'll get either the positive or negative root of 1 minus cosine theta over 2, where instead of having both the positive and the negative, usually the context of the problem will help tell you where you need to be, meaning what quadrant the angle lives in. So let's take a look at a quick example of how these might be used. Suppose you know that the cosine of 210 degrees is negative root 3 over 2. This is something you know because 210, if you graph that, has a reference triangle and a reference angle that's familiar to us. We'd like to now try to use this information to find the exact value of cosine of 105. This is an unfamiliar reference triangle. Well, let's draw a picture and see what's going on here. So what we see here is 105 will live somewhere in quadrant 2. That's going to be 105 degrees. So here's our reference angle. All right, we have A, S, T, C. We know now that cosine of 105 degrees, since we live in quadrant 2, we see that this is going to be negative. So that's going to inform us when we take our root, whether we want to take a positive or a negative root. Which root do we want to take? Or what are we taking the root of, I should say? Well, the cosine of 105 degrees is equal to the cosine of 210 degrees divided by 2, which the half-angle formula for cosine tells me that that's equal to the positive negative square root of 1 plus the cosine of theta, which in this case is 210 degrees, over 2. And since our cosine of 105 degrees needs to be negative since it lives in quadrant 2, that's the choice we end up making. Since that needs to be negative, we take the negative root. So this is then equal to the negative square root of 1 plus negative root 3 over 2, because that's the cosine of 210, divided by 2. And this looks like an ugly number, but it's still just a perfectly valid number nonetheless. We can verify trig identities using the half-angle formulas. For example, we can run up against tangent of theta, something very simple looking, can also be rewritten as sine 2 theta over 1 plus cosine 2 theta. The best way to recognize what's happening here is to start with the complicated side, that's the bit on the right. Let's write that down. So the sine of 2 theta over 1 plus the cosine of 2 theta, what's that equal to? Well, let's look at our half-angle formulas. Take a look right here. Sine of theta over 1 plus cosine theta is equal to the tangent of theta over 2. And this is true for any theta. So what I'm going to do here is I'm going to think, instead of this being a theta, I'm going to think of it as a theta, or as a 2 theta. So thinking of this theta as a 2 theta, this expression will be equal to the tangent of 2 theta over 2. So this is going to be equal to the tangent of 2 theta over 2, which those will cancel, and I'll just get tangent of theta, which is what I wanted. So with the addition of all these trig identities, we are unlocking so many additional, more interesting trig identities. Certainly, this is the type of trig identity that no one would have thought is true. We can do additional interesting trig identities, like the fact that the tangent of theta over 2 is simply the cosecant minus the cotangent. Best way to recognize that is to go back to your half-angle identities. And instead now, when you look at tangent of theta over 2, don't use the last identity, but use the middle identity. Because here you can get a common denominator. So using that identity, we can get...
Okay, I found this on the web for can get a common denominator.
Siri interrupting my lectures. So using that identity, we can end up with the following. The tangent of theta over 2 is equal to 1 minus the cosine of theta over the sine of theta, which, I think I did this earlier in the lecture, right? We're thinking of this as one fraction minus another fraction. And so I can rewrite this as 1 over the sine of theta minus the cosine of theta over the sine of theta, which of course translates into what we're looking for, which is the cosecant of theta minus the cotangent of theta, and we're done. So again, we're unlocking so many new trig identities. While we're on the tangent of theta over 2 train, let's even get more creative with it. Here we have the same thing, tangent of theta over 2, but now the right side is way more complicated. Since it's so complicated, maybe I'll start with that when I try to verify my trig identity. So we're going to take the right-hand side, which is the secant of theta over secant of theta, cosecant of theta, plus cosecant of theta. I'm just going to turn everything into sines and cosines. We'll get 1 over cosine divided by 1 over sine cosine plus 1 over sine. And now the denominator needs a common denominator, so we're going to give this fraction over here on the right a cosine over cosine. And that'll convert this entire thing into a 1 over cosine of theta, all divided by 1 plus cosine of theta divided by sine theta cosine theta. And now we have a fraction over a fraction, so we can use keep change flip, and we can turn this into sine of theta cosine of theta divided by cosine of theta times 1 plus cosine of theta, for which these two cosines will cancel. We'll end up with just sine theta over 1 plus cosine, which we might recognize at this point. Sine over 1 plus cosine is exactly this third representation of tangent of theta over 2. So we see that indeed this is going to be equal to tangent of just theta over 2, which is exactly where we want it to be. Let's end off section 5.3 here with one last trig identity. And that trig identity is going to be, well, so we looked at sine of 3 theta before. So let's see if we can't do better. Let's try, say, sine of 4t. There's actually a lot of ways to proceed to try to assert that this identity exists. So again, if you want to pause and take a crack at this, I encourage you to do so, because there's a lot of ways to get there, and your way might differ from mine, but it might even be a better version. Nonetheless, I'm going to work through it as well, so if you want to pause and follow along, or sort of pause and unpause, that way you can get sort of tips from seeing what I'm doing, I encourage that as well. The way I'll proceed is to start with the left-hand side, and we have options. We could, for example, try to rewrite this as sine of 3t plus t. Using a sum formula for the sine of 3t plus something, we could rewrite this as sines and cosines involving 3t and t. And we already figured out a formula for 3t. So that might be a good way to go. But I think there's a faster way to do this. Instead of decomposing 4t as 3t plus t, let's go ahead and decompose it as simply 2t plus 2t. Using the sum formula for sines, this is the same as writing it as sine of 2t times cosine of 2t plus sine of 2t and cosine of 2t, which of course, these are the same thing. So this can be rewritten as 2 sine of 2t cosine of 2t. Which, by the way, parenthetically, there was yet another way that one could have started this. You could have written sine of 4t as simply sine of 2 times 2t, but that's just an angle in and of itself like alpha, so this is the same as sine of 2 alpha, which we know that by the double angle formula, this is equal to 2 sine of alpha cosine of alpha, which, because alpha is equal to 2t, this is the same as 2 sine of 2t cosine of 2t, which is exactly where we're at currently. So like I said, there's lots of ways to proceed here. But let's get back to what we'd written. Here we have sine 2t and cosine 2t. We do have double angle formulas for what those are, so we could write this as 2 times sine of 2t could become, like we said earlier, 2 sine theta cosine theta. And the cosine squared, we have options, but I'm going to go with the base formula, which is cosine squared theta minus sine squared theta. And then, if I pull all this together and distribute, what I'll end up with is 4 sine theta cosine cubed theta minus 4 sine cubed theta times cosine theta. Which, by the way, is where we want to end up. But there's actually more to this. We're actually scratching at the surface of a very interesting line of argumentation that we could go down. Because observe that when we did sine of 4t here, we got sine and cosine, and there's 1 sine, 3 cosines, 3 sines, 1 cosine. The sum of the powers are adding up to 4, and there's 4s sitting out front. Let's go back to when this was a 3t. Let's see what happened. That was, here it is. What was the final answer? We had here 4 and a 3, and then here's a 3 and a 1. Now, of course, this has sines only, without any cosines. So if we do come back a couple steps, here we might take a look at this step. Here we have sines and cosines, and their sum is still 3. But we're missing the 3 in front of the sine cubed. So it might be hard to sort of take a look at what the pattern is, but if you have some free time and you want to keep messing around with this is a process to do sine of 3 theta. What we just took care of down here was sine of 4 theta. You could try sine of, say, 5 theta, and then do sine of 6 theta. Do enough of them, and I promise you're going to start to notice a pattern. If you do notice any of this pattern, send me an email or drop by an office hour, and I'm happy to talk to you about sort of what the underlying math is behind the pattern that you see. It's really quite interesting and rather deep as well. Nonetheless, that's where we'll wrap up section 5.3. Next video, we're going to continue this packet and finish this packet with a discussion of section 5.4, which is going to be the final collection of trigonometric identities that we're going to encounter. And those are going to be called the product to sum and the sum to product formulas. So I'll catch you all in that video.